Alright, hello everybody, and today we're going to be doing an example of first principles on a specific function. But first of all, let's try and remember what first principles was. Remember that we had this limit at the start here. A limit as some h approaches 0, and we had something over something, and you can remember this as rise over run. So our rise was the difference between the outputs of our 2 points. So if you imagine some curve and you have the x coordinate of this point as being x, well, the output is just f of x. And if you have some point close by, that's a distance of h away, x plus h, then the y value will just be f of x plus h. So the rise is just the difference between whatever these two values happen to be. So you have f of x plus h minus f of x. And the run is just this h right here. So we have h on the denominator. Alright, cool. And just to reiterate one thing here, the reason why we have this limit is we don't want an approximation for the gradient of our curve. We want the actual gradient of our curve, not just any random approximation. So today we're going to be having a look at first principles on the function f of x equals to x squared. So using first principles here, we want to find maybe a new function that can tell us the gradient at every single point on our x squared graph. So remember, our x squared graph is just a simple parabola like so. And we want to be able to find some function that can tell us the gradient of our curve x squared at every single point. Alright, so let's have our try and substitute our function f of x into our first principles here. So first of all, we have the limit as h approaches 0, because we don't want an approximation for our gradient, and f of x plus h. Well, notice f of x, it's taking in whatever input it's getting, and it's just squaring it. So f of x plus h must be the input, x plus h, but squared. And of course we have f of x here, which is just x squared, so we're subtracting x squared, and we're dividing everything through by h. Alright, so this might not seem too interesting, but let's try and manipulate this equation a little bit. Let's start by expanding out this squared term right here. So we now have the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared, and everything divided by h. And notice that this x squared and this x squared will cancel each other out. And now all that we're left with is the limit as h approaches 0 of this numerator here. But notice that this numerator here has a common factor of h that we can factor out. So let's pull our h out, and what we're left with on the inside is just 2x plus h. And everything's being divided through by h. And notice that this h and this h here can cancel each other out. And even though h is tending towards 0, we can still cancel the h's out because we're kind of thinking like h approaching 0. And so h is still some kind of finite number we can work with. So that's why we can cancel them out here. So now we're left with the limit as h approaches 0 of 2x plus h. And what does this mean right here? Well, if you just take a look at this part on its own right here, this will be the gradient of a secant line depending on your x values. So depending on where you choose your x to be, and depending on what your h is. And remember, your h kind of controls the distance your 2 points are away from each other. But we don't want an approximation. We want the actual gradient. That's why we have this limit right here. So as h gets smaller and smaller and smaller, what will happen to this expression right here? Well, h will get so incredibly small that it just becomes negligible. It just pretty much disappears off to 0. So all that we're left with is 2x. And what does this 2x have to do with our original x squared here? Well, this new 2x here, we can use this function to find the gradient at any given point x on our x squared graph. So for example, this is our x squared graph here, and if we want to find the gradient at the point x equals to 2, so we want to find this tangent line kind of right here. Well, all we need to do is plug 2 into this function right here to get 4. So that means the gradient of this line here, of this tangent line, is exactly 4. And let's say we wanted to find the gradient on x squared at the point, let's say, -1. Well, that means finding the gradient of a tangent that passes through -1 right here. So just plugging -1 into this new function here gives us -2. So -2 is the gradient of this line right here. So what we refer this function to in terms of our original function, we call this thing the derivative of x squared, because this new function here kind of came from our original function after we did first principles. So we can think of first principles as being a tool we can use to find the derivative. Another name you might hear this called is the gradient function, because this function can tell us the gradient of this original function at any given point. So you may often hear this referred to as the gradient function. So how about let's now graph both of these functions here and see how they behave side by side. Alright, so I've graphed out y equals x squared and also its derivative, which is y equals 2x. And let's have a look at some of the properties these two graphs share. So first of all, let's take a look at the gradient of our x squared graph right here. Notice that on the left hand side here, what is the gradient of this curve right here? Well, notice it's kind of pointing down that way, which means it's negative all throughout this left branch here. However, on the right hand side, the gradient becomes positive. And how about 0? Well, at 0, the gradient is exactly 0. So how is the gradient of our x squared graph reflected on our new derivative graph of 2x? Well, if you look at the negative values of x here, what does our function 2x spit out? Well, as you can see, it only spits out negative values of x because our line is in the negative region. However, if you look at the right hand side, or the positive values of x, our graph of 2x is always positive. And what that corresponds to on our x squared graph is the left hand side being a negative gradient and the right hand side being a positive gradient. Also, our 2x graph here is exactly 0 at the point x equals 0, and that corresponds to our y equals x squared graph having a gradient of 0 right at x equals to 0. So you kind of see how these two graphs relate here. When our derivative is negative, which means it's below the x-axis, that corresponds to the gradient of our original function x squared here being negative. And when our derivative graph here is above the x-axis, or it's positive, that corresponds to our original function here having a positive gradient. And whenever it's exactly 0 right here, when the y value of our gradient function is 0, that just means that we have a stationary point right here. Or in this case, it's a turning point on our x squared graph. And pretty much that's when the gradient is 0. So just to recap what we just learned here, we used first principles to find the derivative of x squared, which happened to be exactly 2x. And what does the derivative tell us? Well, plugging in any values of x into our derivative here will give us the value of the gradient of our original function. So if you imagine plugging in an x value of 5 into our derivative here, well, our y value will just be 10. And what does that mean? Well, that means the gradient at the point x equals to 5 on our x squared graph is 10. So the gradient at this point is 10. And that is reflected on our derivative. So we can say that the derivative of our x squared graph is 2x, because 2x kind of came from x squared via first principles. So we can use 2x as a function to find the gradient at every single point on our x squared graph. And that's pretty cool if you ask me. We have this new method of first principles here to find functions that represent the gradient of another function. So that's pretty much all for this video right here. Next video, we're going to be going over some notation for the derivative and how to write it out mathematically. So that's pretty much all for this video, and I'll see everyone next time.